Hi, welcome to part 3 on interval of convergence. Now in part 1 we talked about how to find the radius of convergence. In part 2 we started talking about how do we find values of x that will make sure that this series will converge. For example, like remember that if I don't have this polynomial part, this series will converge by our alternating series test. So we know that there are values for x that will make this converge. Likewise, there are values for x that will make this series diverge. We just have to find those. Before we begin, though, I don't want you to have to panic. This is a Taylor polynomial. And this is how we write a Taylor polynomial. Remember, this is just the nth derivative at c over n factorial times x minus c to the n. There's my x minus c to the n. So there's my polynomial part. This part right here is generated by our Taylor part. Remember, we just called that a sub n in part 1. So what we first have to do from part 2 is to look at the radius of convergence. We have to find that radius. To do that, we use our ratio test. So remember, the ratio test says we're going to take the the next term, the a sub n plus 1 term over the a sub n term. So to do that, very simple, we take negative 1, this becomes n plus 2, times x minus 5 to the n plus 1, over, be careful, n plus 1, 5 to the n plus 1. Now I'm going to divide it by a sub n. Remember, it's a sub n plus 1 over a sub n. But I don't want a complex fraction, so I'm just going to invert and multiply already. So this becomes n times 5 to the n over negative 1 to the n plus 1 times x minus 5 to the n. We know this has to be less than 1. We know that. So because the ratio test says if this is less than 1, this series will converge. So I'm going to simplify this. A little bit of algebra goes a long way. We're going to be left with 1, negative 1 on top. Looking at the x minus 5s, looks like we'll be left with an x minus 5 on top as well. Looking at the n's, really can't simplify those, so I'm left with an n on top and an n plus 1 on bottom. Looking at the 5 to the n's, it looks like we're left with a 5 on bottom. This must be less than 1. Now, from part 1 and part 2, we talked about we're looking at n goes to infinity. So anything that does not have an n to it, we can just kind of pull it out. We're just going to take those all out. And what I'm left with is, now if I take the absolute value, that negative 1 just goes away. So I'm left with the absolute value of x minus 5 over 5 times the limit as n goes to infinity of n over n plus 1 has to be less than 1. We didn't see one of these in part 1, did we? If I let this limit go to infinity, this is just Bobo-Botten. This whole term just becomes 1. And what that leaves me with is this absolute value of x minus 5 over 5 is less than 1. Now, you got to be careful. We're centered around 5 this time. Sorry, we have this. We're centered around 5. Sorry, we got this 5 on bottom here this time, which we didn't see about in part 1 or 2. Excuse me. Excuse me. Man, I'm allergic to really challenging problems. So, what we're going to do is we're going to multiply both sides by 5 here. So therefore, we get this absolute value of x minus 5 is less than 5. Now, this 5 right here, you may recall, that's our radius. So we already have the radius of convergence. It's 5. And what it says is we're 5 units away. Anything within 5 units of our center is the series will converge. Well, how do we get the center? Well, that's what this is. From our Taylor polynomial, x minus 5. X minus 5. This comes from our Taylor polynomial. So we know that the center, which we said was c, is going to be 5. Now, graphically, what does that mean? If I'm here at 5, if I go over my distance, my radius, plus 5 units away, I'm at 10. If I go minus 5 units away, I'm at 0. So we're saying anything between 0 and 10, this series will converge. And we can kind of show that algebraically, right? We got the absolute value of x minus 5 less than 5. So we get negative 5 less than x minus 5 less than 5. So we're saying x is between 10 and 0. Now remember, this is only a possible, we call this a possible interval. To get the actual interval, we do have to check our endpoints. So the first endpoint we have is 0. And I'm just going to plug it into the original series up here. Okay? N equals 0 to infinity, negative 1 to the n plus 1, and 0 minus 5 is negative 5 to the n over n times 5 to the n. Now a little bit of algebra from 0 to infinity. If I pull this out, ready? This is really saying negative 1 to the n times 5 to the n. So if I have negative 1 to the n and negative 1 to the n plus 1, we get negative 1 to the 2n plus 1 times 5 to the n. Those cancel. This is the hardest one there is, which is going to equal from 0 to infinity. Now, if you notice, this is always just going to be negative. So we're going to get a negative 1 over n. Ignoring the negative, really, this is just a p series. P is 1, therefore this series diverges by p series. So therefore, x cannot equal 0. But we do have to check our other endpoint. The other endpoint was 10. Well, if I plug that in, this one's going to be much easier. Negative 1 to the n plus 1. If I plug 10 into my original, 10 minus 5 is 5. So this becomes 5 to the n over n times 5 to the n. Cancel, cancel. 0 to infinity, we get negative 1 to the n plus 1 over n. Notice this is alternating series. This is alternating and decreasing. So therefore we can take the limit as n goes to infinity of 1 over n, we get 0, which is what we want. Therefore this series converges by alternating series test. So what does that mean? X couldn't be 0 because it diverged. X equals 10 converges, so x can equal 10. Now what all does this tell us? Well, we got the radius earlier, was 5, and our interval now, very simple, it starts at 0, ends at 10. But in this case we can include the 10. And that's how we get our radius and interval of convergence. See, it didn't take long, only 8 minutes. Now, I have one last example for you. This is an easy one. Number 4. Okay, this is number 4. What happens if we get something like this? From 0 to infinity of n factorial x minus 3 to the n. Just kind of a quick one right here. Well, I want to find the radius, so I let n go to infinity. So this is going to become n plus 1 factorial x minus 3 to the n plus 1 over just n factorial x minus 3 to the n. Has to be less than 1. And if I take a look here, let's see here, we simplify a little bit, n goes to infinity. Right, this is just n plus 1 times n factorial. Those cancel. We're left with n plus 1 on top and an x minus 3 on top. Nothing on bottom this time. This has to be less than 1. Well, if I factor out that x minus 3 times the limit as n goes to infinity of just n plus 1 less than 1, this shoots off to infinity. The limit then goes to infinity, so it gets bigger. So what we're saying is infinity is less than 1, which is obviously false. Now we talked about this in part 1, but what does this mean in terms of our radius and interval? Well, it does, remember what this tells us in part 1, that this will diverge always. This will diverge always except, and in part 1 we talked about this, except when our radius is 0. We talked about why that is. If this is 0, my radius is 0. If this is 0 right here, it'd just be 0 plus 0 plus 0. It converges to 0 if you add it all up. So we have to set our radius equal to 0. Well, how do we get our radius? That's just this x minus 3. So to get the radius, we take this x minus 3, set equal to 0. This will converge if x equals 3. So it does have a radius. It's 0. It even has an interval. It's not a small one, a real small one. X equals 3. So there you go. This is interval and radius of convergence, one of the more challenging things, but you know, this is on the AP test. You do want to practice these, okay? Bye-bye.